This lesson deals with Supplemental Problem 4.5. You can find this problem in the course ebook in the Chapter 4 Supplemental Problems on page 4. In Chapter 5 lecture notes on page 27, I did a derivation of a complete response for this circuit, which shows the transient analysis and then the forced response. This was actually a two-page derivation. I didn't show all the work, but it is quite tedious to be able to solve for the complete response. But in most cases, all we care about is the steady state response. And we have a technique for doing this in Chapter 4. So let's find the steady state response, which is also called the forced response, using our phasors and the phasor techniques. Our three-step algorithm is first to transform the problem from the time domain to the frequency domain. A resistor is still a resistor. A capacitor, though, becomes an impedance of 1 over j omega c. And our current source, which was a cosine function, is going to have a magnitude, I sub a, and an angle of 0. We're trying to solve for this voltage V of t in steady state. And that would be the voltage, our phasor voltage here. One way to find that is to find the total impedance seen by these terminals of the current source, and then just multiply that by the current. You have the parallel combination of two elements. That would be the product over the sum, R Thevenin times 1 over j omega c, divided by R Thevenin plus 1 over j omega c. Multiply numerator and denominator by j omega c. That cancels with this, and you just get R Thevenin, and then you get j omega c times R Thevenin, and then plus 1. Because we're going to multiply, let's put this in polar form. The numerator is just a constant, so that would be the magnitude of R Thevenin at an angle of 0. The denominator, though, has got a real and imaginary part. Well, the magnitude is the square root of the sum of the squares. Square the imaginary part, going to give me omega squared, and then c and R Thevenin squared, plus 1 squared, and then square root. The angle is the arctangent of the imaginary part divided by the real part. The arctangent would be of omega c R Thevenin divided by 1. That's that term. So V is equal to our phasor current, I sub a at angle 0 times Z equivalent. Here's I sub a, and here's my Z equivalent. The overall magnitude is the product of the magnitudes divided by the denominator magnitude. That's this term. And the angle is 0 plus 0 minus the angle of the denominator. So this is our frequency domain result. Step 3 is transforming from the frequency domain to the time domain. Here's my amplitude. Here's my angle. Let's put the cosine of omega t between the two. In the formula up top, we have a tau term showing up. Tau is equal to R Thevenin times c, or you could say that R Thevenin is tau divided by c. In this expression over here, I have I sub a and R Thevenin. I'll replace that by tau over c. This expression here, I've got omega squared, and I've got c R Thevenin, but again, R Thevenin is tau over c. We're going to square that, so the c's will cancel. I get tau squared times omega squared, and plus 1. Cosine of omega t. Here we got omega, and then c times R Thevenin, but again, R Thevenin is tau over c. The c's cancel, we just get tau times omega. That's the same expression we have on top. It's the forced response when we solved for the complete response by solving the differential equation. And this is Supplemental Problem 4.5.